So our next speaker is Inhyeok Choi at KIAS, and he talks about genericity of contracting elements in groups.
Okay, first, thanks for having me here. I thank all the organizers to um, prepare this wonderful chance of meeting, and especially to Hyojang for inviting me. So today, I'm gonna talk about some bit of geometric group theory and perhaps geometric topology, but mainly in the theme of geometric group theory. So I will first introduce some objects and then explain some phenomena and then phrase them into a result, and then that's it. So today's a goal or um, a meta statement is like this. Hyperbolic groups mainly consist of hyperbolic elements. Well, depending on the preciseness that you pursue, this might sound quite trivial or quite nonsense in some sense. So, but to make this precise, we should first discuss what hyperbolic group is, what hyperbolic elements are, and also what I mean by merely consisting of. Okay, let's get started. So I work in geometric group theory, and like as well as you, most of the audience, I assume. So, but just to recap, the geometric group theory concerns um, geometric properties of various groups based on their actions on spaces. So in geometric group theory, the geometry and the actions are quite quintessential. Like they cannot be discarded. We always have them in mind. So for example, when we study the set of integers or the grid, like z square, or finite groups, or like some matrix groups such as GLN or SLN, and also more generally Lie group or lattice, or various automorphism groups, diffeomorphism groups, and blah blah blah. Like whatever objects you have in mind, you always associate them with their actions on a space, like the grids or the projective space or the covering space of a manifold, and so on. And often the details, the precise, for example, differential geometric details of the space seldom matters when you want to describe a large-scale geometry of the space or the associated group. And there are some efforts toward axiomatizing these, like these large-scale properties, ignoring the details. And two notable notions are Gromov hyperbolic spaces that are defined by Misha Gromov, and cat-zero spaces, which is a slight generalization of Adamar space, or like in differential geometry. So these can be regarded as a GGT version of negatively curved spaces, or more generally, non-positively curved spaces. So these are all the efforts of capturing hyperbolic dynamics in the language in terms of GGT. So for example, if you're familiar with this, like for example, negatively curved manifolds enjoy hyperbolic dynamics, so that if you draw like geodesics in a random sense, then they almost surely diverge very fast. And this has lots of ramifications in orbit counting or like description of the phenomenon at boundary or something like that. And they can be in part captured by this kind of GGT language. This is just a digress, but you don't even have to stick to, for example, Riemannian manifold. So for example, if you bring your hyperbolic surface, then there's another way to construct yet another space out of this surface, which is the parameterization parameter space of various structures in the that can be put on this surface. Namely, the Teichmüller space is the set of all marked hyperbolic structure or marked conformal structure on the surface. And this is actually a universal cover of a more of a moduli space of a marked Riemann surface. And the covering transformation group correspond to the famous mapping class group. So if you're interested in mapping class, the geometry of mapping class group, or if you're interested in the moduli space of Riemann surface, so if you came from complex analysis or algebraic geometry, or if you're interested in Teichmüller space itself, what you have in mind is this trinity. Like these three objects are closely related, and then a question on the moduli space, which can which is what is the typical simple closed sorry, not simple closed, what is a property of a closed curve that can be drawn on the moduli space? This is translated into a language of mapping class groups. So what is the property of a typical mapping class? And this conversion of viewpoint has been employed by Mirzahani for the counting the length asymptotics of curves on the surface itself. So we began from a surface, but we constructed another grander parameter space that fits into the term of GGT. And then that gives rise to a concrete description of something on the surface. So this is just to convince you that this perspective is quite fruitful. But today we will stick to more humble and more simple-minded objects. So G is a finitely generating group, and then whatever group that is, we have at least one very canonical space that G acts on, and probably most of the audience will be familiar with this better than me, but this is called a Calligraph. So this Calligraph is made out of vertices, the elements of the groups, and we connect two vertices if and only if they are related by a generator. So we first fix this finite generating set, and then we draw this Calligraph, and then G acts on this graph isometrically. And this action is proper and co-compact. Hence, I can say, okay, it's fair to say that this Calligraph literally contains the geometry of the group. It can be regarded as definition. So when we talk about geometry of the group, by that we mean that we study the geometric property of the Calligraph. A simpler toy example has already appeared in the previous talk by Josiah. So if you have a simplicial complex that's drawn here, so this represents a group generated by four generators with a single relation, the commutative relation. So this will be a free product of Z square and the free group of rank 2. Or you can say that it's a free product of Z, another Z, and Z squared. And if you want to study this group, we can unwind the simplicial complex into a simply connected universal cover, denoted by tilde x tilde. And then you have orbit points. So if you fix a reference point, and if you take the lift of those orbit points, then the geodetic segments between orbit points represent the closed curve on the downstairs. Hence, studying a typical curve on X is tantamount to studying a closed geodesic segments connecting orbit points on the universe cover. And we can ask in this example whether a typical such segment is flat or tree-like. So just to sum up, the metaspaces have some sort of hyperbolicity, and this has been axiomatized by great figures. And groups also have innate geometry via the natural Calligraph. And then we can discuss how hyperbolic a group is by investigating whether a typical geodesic segment satisfies some hyperbolicity property. And then later on, this will be linked to some dynamics, hyperbolic dynamics enjoyed by the element. Okay, so those were the objects, and the phenomena is like this. So, okay, so the prototype were negatively curved manifolds or Teichmann space or those things. And then these were captured by some axioms by Misha Gromov. But we want to rephrase that axiom into another equivalent condition. But that condition should capture some hyperbolic dynamics. This is our motivation. So, for example, if you do a geodetic flow on a hyperbolic plane or a hyperbolic n space, then you can always chop down the tangent space into two directions. One along the geodesic line that you're taking the flow, and the direction is orthogonal to that. And then what you actually have is if you let the flow go, the direction is orthogonal to the flow gets contracted with uniform quality. And this is due to the negative curvature of the manifold. Okay, that's all good. That's quite intuitive, but this is quite differential geometry. You should be able to discuss tangent space and flow and geodesics to describe all this. But how can you discretize? How can you realize them on groups and the calligraphs of groups? If you want to if you want to take an analogy, how would you phrase? And this is one answer given by okay, this was suggested by Minsky for Teichmann space, and Archanseva Kashentau also had a nice theory using this notion, and Sisto also had, and there are plenty of other people. So, but the definition follows. So a geodesy gamma is K contracting if the projection of B, a ball, onto gamma is always small or bounded. So I'll do it 1 second. So the projection has bounded diameter. Denoted by K. So if you bring a constant K, we say the gamma is K contracting if the diameter of arbitrary balls onto gamma has diameter smaller than K. But here, the restriction is B being disjoint from gamma. So if you imagine a hyperbolic plane, if you're familiar with hyperbolic geometry, here's a geodesic gamma, the green line. And if you draw a metric ball that's disjoint from gamma, then the biggest thing you can draw is this kind of thing that's tangent to gamma and the boundary. And then the projection is not like this. The projection is always curved slightly inward so that there's a finite value K that bounds the size of projections of arbitrary ball disjoint from this geodesy. So in H2, it's easier to imagine and also prove. And this holds for a very large class of spaces, including, for example, thick geodesics, the axis of pseudo-concepts on the Teichmann space, or rank 1 geodesics on Cat0 space, and so on. So this is a nice, and what's more, I haven't recruited any notion of tangent vectors or whatever. So this really suits to arbitrary metric spaces, including Calligraph. And the fact is, a metric space is Gromov hyperbolic if and only if. Oh, I didn't spell out the definition of Gromov hyperbolic space, but in 3 words, Gromov hyperbolic spaces are where if you draw any if you draw any geodesic triangles, they are uniformly thin, which means they are up to finite error, looks like a geodesic on a tree. So it's really like tree-like space when you deal with finite points, geodesic segments between finite points picked in that space. And a metric space is, as such, Gromov hyperbolic if and only if every geodesic is strongly contracting. That means it shows this kind of contraction. If you draw any ball disjoint for gamma, they project onto a bounded diameter. So this means that axis hyperbolic if and only if each direction is shows some hyperbolic dynamics. So this is somewhat definitive statement, but I will soon show you another probabilistic formulation which allows you some room of error, but that error is controlled. Okay, now I will describe counting. So recall the example of this this group, this simplicial complex and its universal cover. And as I drew here, so there are lots of orbit points, and each orbit point, so in the Calligraph, each orbit point will correspond to each element, G1, G2, G3, blah blah blah, in the group, and then how can we sample those? Sorry, lattice. I wrote lattice point, but I will say orbit points. Orbit points on X, or in our case, for Calligraph, or we can say elements of G. There are 2 competing notions. First, you can probe them via random walk on the group. So you randomly choose which direction you pursue at each step, and then you just repeat. You just take the convolution. That's one way. I will not go into that today. The second way is truncation. Since usually the groups we have in mind are infinite, so we cannot deal with infinitely many elements all at once. So we first collect finitely many of them according to some criterion, and then describe the typical property enjoyed by those elements, and then see the asymptotics by allowing weaker and weaker criterion. Written down more formally, it goes like this. Let G be a countable group. For us, finite generated countable group of isometries. We can, and let P be a property. Presumably, this will be a property that captures hyperbolic dynamics. And then we among those elements such that the norm of G is smaller than R, I collect those elements that satisfy the property and then compare the population. So among those elements in the ball of radius R, if those satisfying P dominates, then we can say that P is a typical property enjoyed by the group G. And if not, it's not. So this kind of problem has been formulated in various settings, and there are some previous works by Joseph Maurer, like Ekman-Taylor, Tiozzo, and Wen Yang. But today, I will stick to the simpler case. So G is acting on its Calligraph, and the property is that the element itself is K-contracting, which means if you imagine the loxodromic isometry on the hyperbolic plane, the orbit follows closely an invariant geodesy. So this is called the axis of the element. And we say that the group element G is K-contracting if its axis on the calligraph is K-contracting. And then among those elements with word norm smaller than R, I collect those that are K-contracting and see how the population decays or increases. And here's my theorem. Joint work with Kunal, Chawla, and Giulio, Tiozzo at Princeton and Toronto. So let G be a non-virtually cyclic finite generated group. So I rule out virtually cyclic case. So these are groups that are almost finite group or almost Z. So this is a technical point, but still. So ruling out those elementary case, if G is hyperbolic, then there exists a threshold K such that K-contracting elements predominate. And if G is not hyperbolic, then you cannot take such threshold. Whatever finite threshold you bring, that K-contracting element will not be the generic case. So this is a sharp dichotomy between Gromov hyperbolic and non-Gromov hyperbolic groups. So this can be regarded as a new characterization of Gromov hyperbolic groups. And this is my final slide. So this is one word pictorial proof. So let's get back to the co-example. So here, the flat-like geodesy. So the segments that looks like belonging to a Euclidean flat is colored by either blue or red segments, and the tree-like very thin directions are colored by black. Then the typical word in this group will be composed of a mixture of black and blue and red segments. And this is like a coin toss. Like you have two possibilities or three possibilities, like one half head and one half tail. And then you just spell out all the possible random combinations of n tosses. Then the typical shape will be not like one half head in a row and then one half tail in a row. It's not plausible. The most typical case will be the mixture of all those heads and tails occurring like consecutively, right? So a typical element will have lots of flat-like subsegments as well as like tree-like subsegments. But the thing is, you can expect that the tree-like or hyperbolic-like segments will will occur in a row for a very long portion. And this is why we expect that if there's a flat-like subsegment, if there's a flat-like segment in the group, then that will occur in a typical element, and this will prevent those elements from being a uniformly contracting element. And the remaining work is actually, this is half cheating because in this example, it's quite visible whether an edge is flat-like, whether it belongs to a flat or not, because this group has quite simple relation. But in a general group, it can be really hard whether this segment belongs to flat or not. You cannot really tell the difference, so you should do better using Wen and Yang's machinery. And that's the end of my talk. Thanks for listening.
Thank you, Inhyeok. Is there any questions to Inhyeok? If not, I have one. In your main
Please.
theorem, yeah,
Mhm.
K depends on like hyperbolicity, constant delta, and n. Like
No, it does not depend on n.
uh-huh,
Sorry.
just
So I
delta.
should have said, so
Oh, I
this
see. Yeah,
tendency, I
yeah.
increase the threshold to cover up all the
Sure.
group
Yeah.
and see the asymptotic. So this K is not meant to depend on n, but definitely, as you mentioned, so if G is hyperbolic, if G is delta hyperbolic, then K can be, for example, 100 delta or something.
Oh, not bad.
Yeah, we
I
haven't
see.
optimized that. Yeah, but still, yeah.
Oh, let's see. And like, are you studying K contracted elements for like non-hyperbolic spaces or
Yeah,
like K0 spaces or?
yeah, in Cat0 spaces. So like there are like contracting elements, but these contracting elements have varying this threshold, varying quality of how strong the contraction is. So yeah, there can be some finer study that can be pursued, but I have not gone through. Yeah.
I see. Okay. Is there any questions to Inhyeok? If not, thanks to Inhyeok one more time. Thank you, Inhyeok.
Thank you.
Thank you.